So knowing that we can calculate the derivative of some scalar valued function in the direction of u by taking the gradient of that function times this unit vector u, how can we find the direction, this vector u, that we should go in to get steepest descent? How can we make the directional derivative as big as possible? Okay, well, the answer is to look at the meaning of the dot product. Remember, if you dot two vectors together, you get a scalar, and that scalar is equal to the length of the first times the length of the second times the cosine of the angle in between them. Now for a given, let's see, first off, u has length 1, so this is just going to be 1. So we have really that the directional derivative is the gradient of f times the cosine of theta. So for a given function, the gradient of f is beyond our control, right? So the gradient of f is what it is. The only thing we can change is the direction in which we go in. In other words, the only thing we can change is this theta. This is the angle between the gradient and the direction we choose to go. And the way to make this as big as possible is to make the cosine as big as possible. And to get the biggest possible, we need to make the angle equal to 0. So, because the cosine is biggest, right, at 0, or at multiples of 2 pi. Biggest possible is going to occur at theta equals 0. So we're saying that we have some function, right, and here in the input space, we want to go in some direction u, so that the angle between the direction we're going and the gradient vector is as close to 0 as we can. And the way to do that is just to let our unit vector be in the same direction as f. Now it has to be a unit vector, so we're going to divide by the gradient of f. So if we take the gradient actually points us in the direction of steepest ascent. Now if we go in that direction, so if we go in the direction of the gradient of f, then what we get for the directional derivative is the gradient of f dotted with the gradient of f over the length of gradient of f, which is going to be the gradient of f, let's see, squared, because gradient of f dot gradient of f would be length gradient f squared, all divided by the length of the gradient of f, which, if we reduce, is just equal to the length of the gradient of f. So the length of the gradient of f is the maximum slope. So we go in the direction of f, of gradient f, then we get the biggest slope, and the biggest that slope can be is the length of the gradient. Now if we wanted to get steepest descent, we should go in the opposite direction, right? If we go in the opposite direction, then theta is going to be 180, so the cosine will be -1. We'll get the most negative value that's possible from this directional derivative. So steepest descent would just be in the opposite direction, opposite to the direction of steepest ascent. Let's look at an example. We've got this function, and we're at a particular point. We want to find the direction that we should go in so that we can increase most rapidly, and then figure out what's the maximum value. So we know that for steepest ascent, so if we want to, let's see, ascent, steepest ascent, we need to go in the direction of the gradient. So we calculate the gradient of our function, and then we'll evaluate it at our particular location. The gradient would be, the first component would be the derivative with respect to x, which is going to be 2xy plus the derivative of e to the xy with respect to x is going to be y e to the xy times the sine of y. Let's see, then our partial derivative with respect to y, see the derivative of x squared y with respect to y is going to be x squared, and then the derivative of this is going to require the product rule. So we'll get the derivative of the first, which with respect to y is going to be x e to the xy times the second, plus the first, e to the xy, times the derivative of the second, which is cosine y. So there's our gradient. At our particular location, 1, 0, then the gradient of f, let's see, if y is 0, that disappears, right? And this disappears, so we get 0. And then that's going to be 0, and that's going to be 0. So we're going to get e to the 0 times the cosine of 0. So the gradient is going to be equal to 0, 1 at our particular location at this point, 1, 0. So what is, this is already a unit vector. So this is the direction of steepest descent. It's the direction that we should go in input space in order to get the greatest increase in our output. So this is the direction of steepest descent. And then the next question is, what is the value of the derivative of f in that direction? Well, we already showed that the directional derivative is equal to the gradient of f dot the direction. So if we're going in the direction of steepest ascent, then we're taking the gradient of f dotted with the gradient of f over the length of the gradient of f, which we saw simplified to be the length of the gradient of f. In this case, the length of the gradient of f is 1. So this is now the value of the derivative in that direction. So for every 1 we go over in this particular direction, the output increases by that number 1. So this is the value of the derivative. So df in the direction of the gradient. Finally, what direction does f decrease most rapidly? Well, if it's most rapidly increasing when you go in this direction, then it's most rapidly decreasing in the opposite direction, which would be 0, -1. So that gives the direction of steepest descent. Let's do another example here. Now we have a function of 3 variables, and so we want to see what is there a direction u in which the rate of change of the temperature function is -3 degrees Celsius per meter. Okay, so our inputs are lengths in meter, and our output is a measure in degrees Celsius. So what we want to do is we want to figure out, okay, what is the derivative of our function t in the direction of some vector u at a given point 1, -1, 1. So remember, to do that, we'll take the gradient of t and dot it with our unit vector. So we need to calculate first the gradient of t, which the derivative with respect to x is 2y, the derivative with respect to y is 2x minus z, and the derivative with respect to z is minus y. Now at our particular location, we're at the point 1, -1, 1. So we plug that in, we have -2. If x is 1 and z is 1, then we have 1. And now we have, what, let's see, if we plug in -1 for y, then we get 1. Now the maximum rate of change is going to be equal to the length of the gradient, right? That tells us the maximum steepness. And the length of the gradient at this particular point is the square root of 4 plus 1 plus 1, which would be the square root of 6. Now our maximum steepness then is only the square root of 6. Let's see, and the square root of 6 is less than 3. It's only 2 point something. Okay, so this is definitely less than 3. So if our maximum rate of increase is 3, our maximum is if our maximum rate of increase is less than 3, our maximum rate of decrease is greater than -3. So the answer is no. So maximum, no, because maximum rate of decrease is the opposite of the length of the gradient, which is the opposite of root 6, right? Which is greater than -3. So we just, the length of the gradient measures the maximum possible rate of change, right? And so the maximum possible rate of increase is root 6. If you go in the opposite direction, you just get the opposite value, -root 6. We can't go down any faster than that, and so we won't be able to do it.